Good morning, everyone. My name is Khushi from BSc Chemistry Honors, second year, and today our chapter is Aldehydes and Ketones. Introduction. Aldehydes and ketones constitute two isomeric series of compounds, both of which contain the carbonyl group in their molecules and are therefore collectively known as carbonyl compounds. Carbonyl compounds. C double bond O. Aldehydes have one hydrogen atom and one alkyl or allyl group linked to the carbonyl group, while ketones have two alkyl or allyl groups attached to the carbonyl group. They are referred as aldehyde group and the ketonic groups. Structure of carbonyl compounds. The carbon oxygen double bond of carbonyl compound is composed of sigma bond and one pi bond. Moreover, in the molecules of aldehydes and ketones, the carbon atom of the carbonyl group is also joined to two other atoms by sigma bond. Thus the carbonyl carbon is involved in the formation of three sigma bond and one pi bond. According to molecular orbital theory, the carbon of these aldehydes and ketones make use of three sp2 hybrid orbitals in forming the 3 sigma bond. As such, these bonds lie in the same plane with angle of approximation about 120 degree between them. The pi bond between the carbon and oxygen is formed by the sideway overlap of remaining half-filled p orbital of carbon with a similar number of orbital of oxygen. The large dipole moments 2.3 to 2.8 dipole of aldehydes and ketones support the polar character of carbonyl compounds. Aldehydes nomenclature. They are named either according to the common name or IUPAC system as explained below. First, common system. Common system. In this system, aldehydes are named after the acids which they give rise to an oxidation. The suffix "ic acid" of the name of acid is replaced by the word aldehyde. Thus, CH3CHO gives acetic acid on oxidation and therefore known as acetaldehyde. Similarly, this structure benzene ring and CHO is known as benzaldehyde. IUPAC names. These names are given in accordance with general IUPAC rules. The longest chain carrying the CHO group is selected. The corresponding word root and the primary suffix are written. This is followed by attaching the suffix al in the place of e. The position. For example, HCHO is formaldehyde, common name IUPAC methanol. CH3CHO acetaldehyde, ethanol. CH3CH2CHO is propanaldehyde and it is propanol. CH3CHCHO isobutyryl aldehyde to methyl propanol. That is all about it. At benzene ring, CH3CHO is p-taulaldehyde for methyl benzene carbaldehyde. Ketones. The two system of naming ketones are common name. Common names of ketones are obtained by adding the word ketone to the name of alkyl or allyl groups present in the molecule. These names are mainly used for aromatic and simple aliphatic ketones. For example, CH3CO, CH2, CH3 is known as methyl ethyl ketone, and the IUPAC name of ketones carry the suffix on and are given according to the usual rules. The longest chain containing the carbonyl group is selected from the name of corresponding hydrocarbon. The suffix is replaced by on. CH3CO CH3 is known as acetone and IUPAC name is propanone. CH3CO CH2 CH3 is methyl ethyl ketone butanone. CH3CO CH2 CH2 CH3 is methyl and propyl ketone. It is pentane 2-ol. That is all about it. Formation of aldehydes and ketones. Formation of aldehyde. Aldehydes are formed during many chemical reactions. Of these we would describe only those important reactions which are actually used for preparative purposes. The first one is oxidation of primary alcohols. Aldehydes can be obtained by the oxidation of primary alcohols. However, this method suffers from a serious limitation because the aldehyde formed are further oxidized to carboxylic acid, that is RCH2OH is RC double bond O and RC double bond OH. Second, special oxidizing agent. The above method of preparing aldehyde involving the distillation of aldehyde from the reaction mixture as soon as it is formed can't be used in the case of higher aldehydes having high boiling point. Therefore, some special oxidizing agents have been developed for preparation. Third reagent we are calling Collins reagent. It consists of complex formed by careful addition of CrO3 to excess pyridine. Pyridine is C5H5N. Corase reagent. It consists of pyridinium chlorochromate (PCC). formed by mixing chromium trioxide, pyridine, and HCl. It is also used in methylene dichloride solvent to convert primary alcohols into aldehydes. Pyridine pyridinium dichromate, which is PDC. It is obtained by mixing pyridine potassium dichromate HCl in SEH2Cl2. Advantages of oxidation of alcohols with above reagents. As it is obvious, advantages of using of any of the reagents is that they restrict the oxidation of primary alcohols to an aldehyde stage. This is because these reagents are used in non-aqueous medium and therefore don't allow the formation of aldehyde hydrates to take place during oxidation. Since aldehyde themselves are not easily oxidized further as aldehyde hydrate, the reaction stops at aldehyde state in the oxidation. Disadvantages also are there. Seventh is Stephen's reaction. Alkyl cyanides on reduction with stannous chloride hydrochloric acid give rise to aldehyde. The aldehyde get hydrolyzed on warming with water to yield an aldehyde. Oxidation of methyl benzene's aromatic aldehydes can be prepared by the oxidation of methyl benzene by the different methods. Riemann-Tiemann reaction. This is a convenient method for preparation of phenolic aldehydes, particularly those in which the aldehyde group is present in orthoposition to that of phenolic group. The reaction is carried out by treating a phenol with chloroform and aqueous sodium hydroxide solution. Formation of ketones. Oxidation of secondary alcohols. Ketones can be easily prepared by the oxidation of secondary alcohols. The oxidation is usually effected by acidified sodium potassium dichromate, potassium permanganate, and chromium trioxide in a variety of solvents. Catalytic dehydrogenation of secondary alcohols. Ketones can be also obtained by the dehydrogenation of secondary alcohols by passing their vapors over copper heated to 475 to 575 Kelvin. Reagents of nitriles with grignard reagent or organolithium compound reaction of an with ether with grignard reagent. Physical properties of aldehydes and ketones. Physical state, with the exception of formaldehyde, which is a gas at room temperature. Formaldehyde is a gas at room temperature. Most of the common aldehydes and ketones are liquid at ordinary temperature. The lower molecular weight of aldehydes have sharp and rather unpleasant smells, but high molecular weight aldehydes and ketones have pleasing smell. In fact, some ketones are used in perfumes. कुछ ketones का used perfume in fact gives pleasant smell. In fact, some ketones are used in perfumes. Boiling points. The boiling points of aldehydes and ketones are lower than those of alcohols and carboxylic acids, and there are no effective hydrogen bonds between aldehyde and ketone molecules or ketones. As such, their boiling points are higher than those of hydrocarbon and ethers of comparable molecular masses. For example, compounds: formaldehyde, acetaldehyde. Formula HCHO CH3CHO. Melting point in Kelvin is 181 and 150. Boiling point is 252 and 294. Type of ketones is acetone, methyl ethyl ketone, which is CH3COCH3 and CH3COCH2CH3 179 187 329 353. Third, melting points. Melting points of aldehyde and ketones do not show any regular trend with increase in molecular weights. Solubility: aldehyde and ketone containing up to 5 carbon atoms are more or less soluble in water, but the solubility falls rapidly with increasing molecular weight. However, members are as well as aromatic aldehydes and ketones are practically insoluble. However, all aldehydes and ketones are readily soluble in organic solvent. The solubility of lower aldehydes and ketones in water is due to the formation of intermolecular hydrogen bonds involving the carbonyl group as shown ahead. Chemical properties of aldehydes and ketones. Aldehydes and ketones are highly reactive compounds which exhibit a marked similarity in their chemical behavior. This is of course due to the presence of carbonyl group in the both type of compounds, but as an important question which arises to us is that what makes the carbonyl compound so reactive and what type of reaction does it bring about in aldehydes and ketones. It would be quite appropriate to deal with this question. Reactivity of carbonyl compound towards nucleophilic attract. The carbonyl compound group contains a double bond between the two heteroatoms carbon and oxygen. Since oxygen is more electronegative since oxygen is Since oxygen is more electronegative than carbon, the bonded electrons, particularly the pi electrons, are pulled strongly towards oxygen. As a result, the carbonyl group is very polar. The carbon being electrodeficient, that is acidic, and the carbonyl oxygen being electron rich, that is basic. Moreover, the carbonyl group is flat and can therefore be readily attacked. Mechanism of nucleophilic addition reaction. The nucleophilic addition reaction to a carbonyl compound is initiated by the attack of nucleophile on the carbonyl carbon. This leads to the formation of a transition state in which the hybridization of carbon shows changes from sp2 to sp3. At the same time, oxygen begins to acquire pi electrons of C double bond or bond as shown. As the pi electrons of C double bond or bond are completely transferred to oxygen, a tetrahedral intermediate is formed in which carries negative charge. This is intermediate picks up a proton. Role of acidic catalyst in nucleophilic reaction. The nucleophilic attack on the carbonyl compound can be catalyzed by the presence of acids. The hydrogen ion generated by rapidly combines with the electron-rich oxygen of carbonyl compound. Relative reactivities of aldehydes and ketones in nucleophilic reactions. The aldehydes and ketones, it is observed that in nucleophilic reactions, aldehydes are more reactive than ketones. Aliphatic aldehydes or ketones are more reactive than aromatic ones. First is aldehydes are more reactive, and then aromatic aldehydes or ketones are more reactive than aromatic one. This can be easily explained in terms of steric and electronic factor. Steric factor: in the transition state of nucleophilic attack on carbonyl compound, the uh, carbon starts forming a bond with the attacking species and tends to form trigonal to tetrahedral state. Now, the larger size of alkyl or allyl group attached to the carbonyl group, the more crowded will be the transition state. As the transition state gets more and more crowded, the steric hindrance of the group increases and the formation of transition state becomes more and more difficult. Thus, the formation contain two alkyl or allyl group attached to the carbonyl group, while aldehydes have one hydrogen and one alkyl or allyl group. As such, ketones would be less reactive than aldehydes. Second, electronic factor. In addition to steric factors, electronic factors are also responsible for greater reactivity of aldehydes as explained. First, aliphatic aldehydes and ketones, alkyl groups have electron releasing inductive effect, and their presence tends to destabilize the transition state by enhancing the negative charge developing on oxygen. Second, aromatic aldehydes and ketones. An aromatic nucleus directly attached to a carbonyl group may be expected to increase the reactivity of aldehydes or ketone as it tend to stabilize the transition state due to electron withdrawing inductive effect. However, the aromatic nucleus stabilizes the reacting aldehyde or ketone even more due to resonance interaction with pi electrons as shown below. Acidity of alpha hydrogen. Beside providing a site for nucleophilic addition to aldehydes and ketones, the carbonyl group is responsible for the acidity of alpha hydrogen. In the presence of a base hydrogen attached to alpha hydrogen, carbon can be split off in the form of plus OH ion. In the absence of base, a hydrogen attached to alpha hydrogen can split off in the form of plus OH to form a carbon, and the carbon and thus formed accounts for many reactions of aldehydes and ketones. The acidic nature of alpha hydrogen and its removal in the presence of a base can be attributed to the fact that the resulting carbon ion is resonance stabilized by the interaction with the carbonyl group as shown below. Nucleophilic addition reaction. A large variety of reactions are shown below. Addition of sodium bisulfate. Nearly all aldehydes and many ketones react with saturated sodium bisulfate solution to form crystalline solids referred to as bisulfate addition compounds. Ketones containing bulky group don't react with NaHSO3. NaHSO3 is sodium bisulfate, and due to steric hindrance mechanism, the reaction involves nucleophilic attack of carbonyl compound by bisulfate, and complete the process of may be depicted as below. Reaction with ammonia derivatives. Aldehydes and ketones undergo nucleophilic addition with the certain compounds to ammonia, such as hydroxyl amine hydrazine phenylhydrazine semicarbonate. The addition compound initially formed eliminates a molecule of water to yield compounds containing a double bond between carbon and nitrogen. Mechanism: all the ammonia derivative represented by the formula H2 and G are basic compounds. Reaction conditions: the control of pH. It must be pointed out that while using an acid used as catalyst in this reaction, it is very important to have proper acidity in the reaction mixture. If the reaction mixture is highly acidic, the hydrogen ions begin to protonate the attacking ammonia derivative to the protonated derivative NH3G. It doesn't have any unshared electrons in nitrogen and is no longer nucleophilic. This naturally means that too much acidity would decrease the rate of reaction rather than catalyze it. In other words, the reaction medium should have just the right acidity or pH about 5 to ensure maximum rate of reaction. Reaction with hydroxylamine. Aldehydes and ketones react with hydroxylamine to form oxyamines. Reaction with hydrazine. Aldehydes and ketones react with hydrazine to form hydrazones. Reaction with phenylhydrazine. Reaction of aldehydes and ketones with phenylhydrazone results in the formation of phenylhydrazones. Reaction with semicarbazide. Both aldehydes and ketones react with semicarbazide, form semicarbozones. Reaction with ammonia. The reaction of aldehydes and ketones The reaction with aldehydes and ketones with ammonia are of no importance. Most of aldehydes initially form addition products with ammonia as known as aldehyde ammonia. Ketones generally give complex polymeric products with ammonia. Reaction of aldehydes and ketones with primary and secondary amine to form imines and enamines is discussed in next chapter. Addition of alcohols. Aldehydes and ketones react with alcohols in the presence of anhydrous acid catalyst to form ethereal compounds called acetals. Acetals contains new bonds between carbon and oxygen atoms of groups. Formation of cyclic acid. Both aldehydes and ketones react with ethylene glycol in the presence of p-taulicene sulfonic acid PTS to yield respectively cyclic aldehydes. Use of acetals and protecting group. Unlike aldehydes and ketones, acetals are very stable to bases but hydrolyzed back to being to aldehydes and ketones upon treatment with acids. Therefore, their formation is used as a means of protecting a carbonyl compound in a certain reaction where it is otherwise interfere with the desired reaction. Protection is the process of preventing a group from taking. Unlike aldehydes and ketones, acetals are very stable to bases but hydrolyzed being back to aldehydes and ketones upon treatment with acids. Therefore, their formation is used as a means of protecting a carbonyl group in a certain reaction where it may otherwise interfere with the desired reaction. Protection is the process of preventing a group from taking part in a undesired reaction by converting it into a new less reactive group from which it can be regenerated at a later stage. The problem can be solved. Nucleophilic addition reaction leading to the formation of carbon bonds. We would first addition of hydrogen cyanide. Hydrogen cyanide add to almost all aldehydes and ketones to form alpha hydroxynitriles, usually known as cyanohydrins. And the second one is mechanism, the reaction which involves the initial nucleophilic attack on carbonyl compound by a strongly basic carbon ion cyanide, and the process is completely by the attachment of a hydrogen ion to the oxygen. Addition of Grignard reagent and other organometallic compounds react with aldehydes and ketones to form addition products which are readily decomposed by preferably in the presence of an acid such as HCl, H2SO4 to yield alcohols. Mechanism in the formation of addition product, the nucleophilic carbon ion portion of the Grignard reagent adds to the carbonyl compound while the remaining portion get attached to the oxygen as depicted below. It may be pointed out that depending upon the starting aldehyde or ketone, the alcohol obtained as the final product may be primary, secondary, and tertiary. Formaldehyde yields a primary alcohol and other aldehydes gives secondary alcohols, while ketones furnishes tertiary alcohols. Addition of salt or terminal alkynes when treated with terminal alkynes in the presence of sodium and liquid ammonia. Addition of sodium salts of alkynes to the carbonyl group takes place. The product form on acidification gives rise to alcohols, which is carbon-carbon triple bond. Mechanism: the reaction involves the nucleophilic attack of carbon ion on the terminal alkynes on the carbonyl group. Reformatsky reaction: the reaction consists in treating an aldehyde or ketone with an alpha bromoester metallic zinc in the presence of dry ether or benzene. The addition product is initially formed as presence in the mineral acid to yield mechanism. The mechanism of Reformatsky reaction is similar to Grignard reagent. Zinc is used in the place of magnesium because organozinc compounds, being less reactive than Grignard reagent, react only with carbonyl group of aldehydes or ketones and don't with the ester. The complete mechanism: aldol condensation: in the presence of dilute base, two molecules of an aldehyde and ketones having alpha hydrogen atom combine to form beta hydroxyaldehyde and beta hydroxyketone. The hydroxyaldehyde obtained is known as aldol, and the process is known as aldol condensation. Cross aldol condensation: aldol condensation can also take place between molecules of two different aldehyde ketones. Such aldol condensation are known as cross aldol condensation reactions, and these mechanisms are given below. Class in stoichiometric reaction. Class in reaction: this reaction is a special case of cross-aldol condensation and may be defined as a base catalyzed condensation of an aromatic aldehyde and an aliphatic aldehyde or a ketone to form alpha beta unsaturated aldehydes. For example, benzaldehyde, benzene ring CHO plus CH3CHO. Acetaldehyde will give benzene ring CHOH, CH2OH. H2O will remove and cinnamaldehyde is our product in the following reaction: benzoin condensation. Aromatic aldehydes which do not contain alpha hydrogen atoms and can't undergo alcohol, however, in the presence of potassium cyanide, they undergo self condensation and the formation of benzoins takes place. Perkins reaction: closely related to the Perkins reaction, which involves the addition of acid and aldehydes to aromatic aldehydes in the presence of bases. Conway reaction: that this is another reaction closely related to aldol condensation. It involves the condensation between an aldehyde and ketone and a compound having an active methylene group such as malonic acid, malonic ester, acetoacetic ester in the presence of base which is usually amine such as pyridine or piperidine. Mechanic reaction: this is a reaction between aldehyde and an amine and an active methylene compound which is usually an analyzable ketone. The aldehyde usually taken is formaldehyde and the amine commonly employed is dimethylamine. The reaction can take place in neutral acidic and alkaline media alkaline media and popularly known as manic base reaction. The mechanism is to start with formaldehyde, react with amine to form an aminium salt. The aminium ion get attacked by the allanate ion on the active methylene compound to form the final product. For example, CH3 whole twice and NH plus CH C2H double bond O. Here H will react with C and the double bond once pi bond will shift towards O, and in resonance CH3 and whole twice and lone pairs will now further will be attached to carbon iminium salt, and the last is iminium ion is formed. The Wittig reaction: this is the reaction between aldehydes or ketones and a type of compounds known as phosphorus yields to form substituted alkenes. The phosphorus yields usually are alkylidine triphosphine phosphoranes, which is C6H53P triple bond C R R dash R and R dash may be equivalent to hydrogen or alkyl or allyl groups. The overall reaction may be represented. Formation of phosphorus yields and Wittig reaction: the phosphorus yields required in the reaction are themselves prepared obtained by the action of a base or unsuitable alkyl triphenyl phosphine halides. The base removes protons from the alpha carbon atom of an alkyl group of phosphonium ion salt to generate yields as shown below. The base generally employed in the above reaction is methyl sulfonyl carbanion organolithium compounds such as N-butyl lithium, phenyl lithium. The solvent commonly used is dimethyl formamide, which is DMF, or tetrahydrofuran, that is THF, tetrahydrofuran, THF, capital T, capital H, and capital F. The yields obtained as shown below are not isolated but are directly made to react with the aldehyde or ketone in the solution. The phosphorus yields a resonance hybrid to following the contributing structure due to negative charge on carbon. The yield exhibit a carbanion character and initiates the nucleophilic attack on carbon. The resulting addition product known as beta undergoes elimination of triphenyl phosphine oxide to yield the alkene directly or via cyclic intermediate as the reaction shown below. The carbonyl compound as well as the yield used in the Wittig reaction may carry suitable substituent, and therefore the reaction can be used for preparing wide variety of compounds containing C double bond O in the desired position. In the case of formation of alkenes which can show geometrical isomers, the reaction gives a mixture of both isomers in which trans iso predominates, halogenation of ionizable aldehydes and ketones. Reduction. Aldehydes and ketones can be reduced to form various products depending upon first reduction to alcohols. Aldehydes can be reduced to primary alcohols and ketones to secondary alcohols either by hydrogenation in the presence of catalysts such as nickel, palladium, platinum, or by reducing agents like lithium aluminum hydride, which is LiAlH4, and sodium borohydride, which is NaBH4. Marin's reaction. Marin-Pondorf validation, commonly used reaction for the reduction of ketones to secondary alcohols. Reduction to methylene group. The carbonyl group in aldehydes and ketones can also be reduced to methylene group to form hydrocarbons. This is generally achieved by following reaction claims and reduction. This involves the reaction of aldehydes or ketones with zinc amalgam and concentrated hydraulic acid acetophenone in the presence of zinc amalgam and HCl is ethyl benzene. The reaction works well for ketones but not for aldehydes. Wolff-Kishner reduction. In this method, the aldehyde or ketone is heated with hydrogen and also potassium hydroxide to potassium tert-butyl. Reduction with HI. Aldehyde and ketone can be reduced to form corresponding hydrocarbon by heating with HI in the presence of red phosphorus. Aldehyde ketone with red phosphorus and HI will give simple alkanes, water, and 2I2. Bimolecular reduction. In the presence of magnesium, usually employed in the form of amalgam, aldehydes and ketones undergo bimolecular reduction to form symmetrical glycols, generally known as pinacols. The name pinacols was initially employed for the glycol obtained from acetone, but it has come to be used for the symmetrical glycols mechanism. Pinacol reduction involves the formation of a bond between two carbonyl compounds and proceeds through the following mechanisms. Magnesium donates one electron to each two two molecules of carbonyl compound to form an adduct. This contains two unpaired electrons, one on each carbonyl compound, which unite to a carbon-carbon to form magnesium salt of pinacol. The salt is hydrolyzed to form the pinacol. Reductive amination. Many aldehydes and ketones change into amines on treatment with hydrogen and ammonia in the presence of catalysts such as nickel. The process is known as reductive amination, probably precedes the intermediate formation. Oxidation. The behavior of aldehydes and ketones towards oxidizing agents constitutes the main difference in chemical reaction. Oxidation. Reducing character. Since aldehydes are very easily oxidized even by mild oxidizing agent, they act as powerful reducing agents. Reduction of tolerance agent. Tolerance agent is an ammoniacal solution of silver nitrate which contains silver in the form of silver ammonia complex, which is AgNH whole thrice positive. This reaction is therefore referred as silver mirror test. Reduction of Fehling solution and Benedict solution. Fehling solution is obtained by mixing equivalent quantities of a solution of copper sulfate and solution of sodium hydroxide and sodium potassium tartrate, known as Rockley salt. The resulting solution contains a copper tartrate complex which furnishes a small concentration of cupric ions. Oxidation of ketones. It has already been stated that ketones are not easily oxidized. Balayar-Villiger oxidation. This reaction involves the conversion of ketones per acid such as perbenzoic acid and peracetic acid. Trifluoroperacetic acid formation of ester takes place due to the introduction of an oxygen atom bet carbonyl compound in an alpha carbon mechanism. The reaction is catalyzed by acid and involves the addition of peracid to carbonyl and carbon of ketone. The most important step in this reaction is migration of group R dash from carbon to electron deficient oxygen as shown below. In case of unsymmetrical ketones, the tendency of the group to migrate, called migratory aptitude, to electron deficient compounds in oxygen is tert alkyl, and then secondary alkyl, then phenyl, then primary alkyl, then methyl, p-methoxyphenyl, p-tol phenyl, p-chlorophenyl. The migratory aptitude determines the final product formed in the reaction. For example, in the oxidation of acetophenol with perbenzoic acid, the final product is CH3C double bond O, C6H5 not C6H5C double bond O, OCH3, because phenyl group has a greater tendency to migrate to electron deficient oxygen than methyl group. Cannizzaro reaction. This is in self oxidation reaction and reduction or disproportionation reaction which is undergone by aldehydes having no alpha hydrogen. It consists in the treating of aldehyde with a concentrated solution of alcoholic solution of sodium, potassium and hydroxide when alcohol or carboxylic salt is produced. Prost-Cannizzaro reaction. Cannizzaro reaction can also take place in the two different aldehydes not having alpha hydrogen. It is also known as cross-Cannizzaro reaction. Can lead to the formation of four different products. However, if one of the aldehydes is formaldehyde, the product consists of almost exclusively sodium formate and the sodium derived from the other aldehyde. Test of aldehydes and ketones and detection between them. Test of aldehydes and ketones can be detected by following. They form crystalline addition products with sodium bisulfate. They form yellow orange derivative with 2,4-dinitrophenyl hydrogen aldehyde silver warming test, but ketones don't. Red precipitate, but ketones don't. Pink color with refrigerant, but ketones don't. In general, aliphatic aldehydes can also be distinguished from aromatic aldehydes by Fehling solution. The former reduce Fehling solution, while the latter do not so. That is all about the chapter aldehydes and ketones. Thank you for listening.